In the late 16th century, the renowned scientist Sir Isaac Newton found himself seated beneath an apple tree in his family's garden. Lost in contemplation, he witnessed an apple detach from a branch and fall to the ground. This event sparked Newton's curiosity, leading him to delve into the laws that governed such phenomena. Newton's subsequent observations and calculations culminated in the formulation of his three laws of motion. Newton's first law of motion, also known as the law of inertia, states that an object at rest will remain at rest until an external force applied on it, and an object in motion will continue in motion with a constant velocity unless acted upon by an external force. Newton's second law of motion describes the relationship between an object's mass, acceleration, and applied force. It states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. Mathematically, this law is expressed as F equals m times a, where F represents the force applied to the object, m denotes its mass, and a represents its resulting acceleration. Newton's third law of motion states that for every action, there is an equal and opposite reaction. This means that any force exerted on an object will generate an equal and opposite force on the object exerting the initial force. Building upon these laws, Newton also formulated the law of universal gravitation. The law of universal gravitation describes the force of gravity between two objects. It states that every particle of matter in the universe attracts every other particle with a force directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Mathematically, this law is expressed as F equals g, m1 times m2 divided by r squared, where F represents the force of gravity between the two objects, g denotes the gravitational constant, m1 and m2 are the masses of the two objects, and r represents the distance between their centers. These scientific laws of motion and gravitation, established by Newton's groundbreaking discoveries, continue to serve as the cornerstone of classical physics. They form the basis for understanding the behavior of objects in motion, from the simplest interactions on Earth to the intricate dynamics of celestial bodies. Newton's work not only transformed our understanding of the physical world, but also paved the way for subsequent scientific advancements, leaving an indelible mark on the history of science.